Imagine you're making dinner. You wouldn't grab a handful of unwashed, dirt-covered vegetables straight from the garden and toss them right into a hot pan. You know the meal would be completely ruined. In data science, raw data works exactly the same way. When we pull information straight from a database or a spreadsheet, it's messy. It has errors, missing pieces, and formats that a computer simply can't digest. We have to prepare it before we can ever use it to train a machine learning model. This preparation phase is the entire focus of Unit 2 in your syllabus. If we look at a recent exam paper, we can see this prep work is heavily tested, with direct questions on concepts like feature engineering, scatter plots, and the machine learning pipeline. The very first step in this prep work is called exploratory data analysis, or EDA. Think of this as laying all your ingredients out on the counter, inspecting them, and taking a quick taste. We are getting a feel for the data's shape and structure before we do any actual cooking. If we skip this inspection step, it doesn't matter how advanced our predictive algorithms are later on. If you put garbage ingredients in, you will get a garbage output. To inspect our data during EDA, our main tools are charts and graphs. But we can't just pick any chart that looks pretty. The chart we choose depends entirely on the type of ingredients, or variables, we are working with. When dealing with a single column of numbers, like student heights, the correct tool is a histogram. It groups individual numbers into bars, so we instantly see which heights are most common. But what if we want to see how two sets of numbers relate, like height versus weight? Adding a second column changes the histogram into a scatter plot. It maps individual points on an X and Y axis to reveal hidden trends. To compare a number against a text group, like test scores across different classroom sections, our data points gather into vertical lanes above the text labels. This forms a box plot, letting us quickly see which sections scored highest on average. Finally, to compare two text groups, like matching eye color against hair color, our chart flattens into a grid called a heat map. The colors shift in intensity to show exactly where those categories overlap most. Choosing the right chart is an investigative tool. It allows human analysts to instantly spot patterns that would remain totally invisible if we just stared at a giant wall of numbers. Once we understand our ingredients, we have to physically alter them so the computer can digest them easily. In data science, this step is called feature engineering. Our first technique is scaling. Imagine cooking a massive potato next to a tiny pea. They won't cook evenly. Scaling fixes this by taking wildly different numbers, like millions and decimals, and mathematically compressing them into a uniform range. Next is encoding. Computers don't speak English, they only speak math. So if we have text labels in our data, like yes and no, we convert them character by character into numbers, like ones and zeros. Then there is binning. This means taking a wide range of continuous numbers and grouping them into broader categories. Instead of tracking exact ages like 21, 23, and 25, we drop those numbers into a single bucket labeled 20 to 30 years old. Finally, PCA, or Principal Component Analysis. If a recipe has 50 spices, you lose the core flavor. PCA filters out redundant noise from a massive dataset, collapsing it so we can focus only on the features with the biggest impact. Feature engineering is the bridge. It translates our human-readable information into a clean, mathematical format that a machine can actually learn from. Now our data is visualized, cleaned, and mathematically formatted. It is ready to be fed into the machine learning algorithm, the actual cooking phase. But getting a prediction out of that algorithm is not the end of the job. Once the model spits out an answer, we have to handle those results through two final steps: interpretation and presentation. Interpretation is an inward-facing task for the data scientist. It means looking under the hood to figure out why the model made a specific prediction. It is exactly like a chef taking a bite of the finished dish and tracing back which spice made it so hot. Presentation is the outward-facing task. This is where you take those complex mathematical findings and explain them to a client or a manager. You drop the technical terms and tell them exactly what the data means for their business in plain, simple language. And that is the complete blueprint for Unit 2. First, you inspect the raw ingredients with exploratory data analysis. Then, you prep them using feature engineering. And finally, after the machine does its work, you explain the finished dish to the customer.